Welcome everybody. Today, now we will continue what we have discussed actually in chapter 4, which is about the conformation of cyclohexane. The first thing we want to continue is simply to study in more details the conformation of cyclohexane. As we have said in the the previous lecture, we said in the cyclohexane actually present in the most stable conformation of cyclohexane is the chair conformation, as you can see it in here. Now, how we draw the chair conformation? Of course, you need to practice how to draw it. I will show you later on, but now for the time being, I will just make the explanation on the board, and then we may go or we may use the model whenever it's needed. I hope you can see the board well. Anyway, this is the chair conformation. This is how we draw the chair conformation. As you can see, these 4 bonds here are the bonds which are on the plane, which are making the sitting of the chair, while this bond here, on the top, this is suppose it's above the plane, this is below the plane. This is how we draw chair conformation. At each carbon, there is 2 bonds or 2 orientation of the bonds. We have axial and we have equatorial bonds. Now, at the axial bond, they are the bonds which are perpendicular to the average plane of the system. Yes, I will. Don't worry. I'm recording by another means, but this is just as a backup plan. I will again record it. Okay. So, now again here, as I said, at each carbon we have 2 types of bonding here. One, we call it axial. These are the green ones, you can see them. These are the axial bonds. Do you follow me? And we do have the equatorial bond. Let's first define the axial bonds. Axial bonds, they are the bonds which are perpendicular to the average plane of the system. The average plane of the cyclohexane, these bonds either to be above the plane or fully below the plane, we call them axial. So axial, they are perpendicular, so let's say like this, to the average plane. Now, we do have another type, which is the equatorial. The equatorial, which are the blue ones here, you can see them. These are the bonds which are oriented either below or above, but they are not perfectly perpendicular to the plane. They are within the plane. It's either above the plane or below the plane. So we have 6 equatorial in general at the cyclohexane, and we have 6 axial bonds. You can see it here. So we have axial, 6 axial, and we have 6 equatorials. The most important thing here, we have alternative orientation of the bonds. In other words, if this axial here, as you can see, this is above the plane, then the equatorial here will be below the plane. The next carbon must be opposite fully. In other words, the axial was above, the next carbon, the axial, will be below. The next will be above. The next below. And the next above, below. So always we have alternation of the orientation. So we have alternation of the orientation of the bonds. Do you follow me, guys? You follow me? So the axial here on the first carbon is above the plane, on the next carbon must be below. The next carbon will be above, and so on and so forth. You follow? So these are actually the most important aspects regarding the cyclohexane. Now, always this geometry or this conformation, the chair conformation, it's not a rigid structure. So this is actually like everything in life is in continuous motion. So we cannot expect that this will take only the chair conformation and so on. But what we mean that within all conformation possible, within all these movements possible for the cyclohexane, the most stable, or most of the time, the structure or the cyclohexane will prefer to adopt this conformation because this conformation is the most stable conformation. Got it? All right, sure. Is this better, Taif? Taif, is this better now? Okay, perfect. As you can see, guys, so as I said, we need just to understand fully the picture. As I said, it's not a rigid structure. It will not take only one conformation, but what we mean, averagely speaking, most of the time, the cyclohexane will prefer to adopt this conformation because, as we explained in the previous lecture, this conformation is the most stable conformation. This conformation will be free of the angle strain. It will be free of torsional strain. Therefore, it will be the most stable conformation. You follow me? All right. So these are actually what I meant here by the axial and equatorial. You can see the axial bonds are the yellow ones. You can see them nicely in this conformation. So they are oriented, or they are perpendicular to the average plane of the chair. So unfortunately I cannot, okay, I must hold it. Now anyway, imagine that the average plane is my hand here. So as you can see, the yellow ones are perfectly perpendicular to my hand here, either above the plane or below the plane. So always, this is above, this is above, this is below. You can see always, as I said, the alternation, what I said here. You see on the first carbon here, we see the axial is above the plane, the equatorial, which is in red color here, is below the plane. The next color, you can see here, the equatorial is above the plane, the axial is below the plane, and so on and so forth. So always we do have this alternation. Do you follow me, guys? Is there any question about the axial and the equatorial and simply the alternation of the axial and the equatorial? Any question? Is there any question?
No question at all.
Sure, thank you. All right, the other issue here which we need to highlight here, that suppose we have big size. Now in the cyclohexane, now I want you just to focus nicely. In the cyclohexane, regardless of all these colors here, all of these are hydrogens. Just these are two hydrogens, so on. So it doesn't matter where the hydrogen will occupy. So at the end of the day, all are the same. All places are the same for the hydrogen. But imagine that we have mono-substituted cyclohexane. Imagine that we have methyl cyclohexane. If we have a methyl cyclohexane, and of course I will just represent the methyl with this eraser. You see, just to show you that this has a bigger size, a huge big size compared to the size of the hydrogen. Now, in this case, the methyl here will have two options to occupy. Either it may occupy the axial bond, which is in this case the yellow ones, or it may occupy the red bond here. Do you follow me? Which you think will be less or more stable situation? The big size atom here, or the big size group here, to occupy axial or equatorial, and why? Which situation will be preferred? Which situation will be more stable? That the big size group should occupy the axial bond or the equatorial bond? And in each case, whatever your answer is, you should say why. Any answer for this question? Any trial? Anyone try? Anyway, I'm just going to write a general rule here for any a bulk group, let's say it here. Let me just write the notice here. Although it's very limited size, space, but what should I do? For any bulk group, it will occupy equatorial more than axial, or balash occupy, it will prefer to occupy. It will prefer to occupy the equatorial more than the axial. That's true. That's true. The equatorial always will be the equatorial. Why? I will show you and prove it to you very easily. Now, as you can see here, above the plane, please focus in here. Above the plane, just focus. This is the chair, you see. Above the plane, how many hydrogens are axial? And write down, please, or speak up. How many hydrogens are axial? Above the plane. How many axial hydrogens? 3. These are the other ones, right? So this is actually what we call it in this chair conformation 1,3 diaxial interaction. In other words, the closest atoms in this structure to each other are these axial atoms or bonds. Do you follow me? So when this big atom, when this big size group, suppose this is the bulk group, what we call it. If this occupies here, axial, what's going to happen, this will be close or closer to these axial hydrogens, and therefore we should expect that the situation here will involve more repulsion forces. Do you follow me? Compared to if this takes any equatorial here, for example, it's far away from this 1,3 diaxial interaction. Do you follow me? So these axials which are above the plane here, these are the axials, what we call it 1,3 diaxial repulsion or relationship. Repulsion. So that's the reason why for any bulk group it would prefer always to occupy equatorial rather than axial, because that means when it occupies equatorial position, the repulsive forces in this situation will be less. You can see it's as if it is outside the system. There is no close atoms to repel this bulk group. Do you follow me, guys? Is that clear? Is there any question? Maria, you have a question, it looks like. Or you are thinking to ask a question. Al-Bara.
Can you repeat, Doctor, please?
Repeat the last information. Al-Bara. So,
yes.
Yeah, the last information we said for any bulk group, it will prefer always to occupy equatorial more than axial. The reason is why? Why, Al-Bara? Because, as I said here, Al-Bara, please focus on this confirmation. What you see here above the plane, Al-Bara, how many axial bonds we have above the plane?
3.
3. Of course, if you look at below, you will see again 3, the same thing. Either if you look above or below, it's the same, right? Now, it means here in this structure, Al-Bara, these atoms are the closest atoms to each other, which means potentially, if you have big atom here, it may make more repulsion forces with these atoms. Do you follow me? If you have any bulk group, what's the meaning of a bulk group? A bulk group, it means any group which has bigger size than hydrogen, which means any other atom than hydrogen. Do you follow me?
Yes.
Any other atom than hydrogen, it will definitely has bigger size, which means potentially it may make more repulsive forces. You follow me, Al-Bara? So,
Yes.
What's the ultimate goal of everything in life, Al-Bara? As we said always, as we keep saying, what's the ultimate goal of any movement, of any action, of any process in life?
Attraction.
More attraction or?
Stability.
No, it's the same meaning. More attraction or less repulsion.
Yes, less
Here we have nothing to do with the attraction, because attraction forces are always the same. But here we're talking about a situation to compare two situations, and of course whenever we have two situations, the situation which includes less repulsion forces will be definitely more stable. Got the point, Al-Bara?
Yes, Doctor.
Perfect. So you can see here, Al-Bara, you can see it by your vision. You see, if this is a bulky group and if it occupy axial, what you can imagine, what you can see, it will be close to these axial hydrogens. This is what we call it 1,3 diaxial interaction. Do you follow me? And that's why we should expect, if the bulky group occupies axial, to be less stable compared if it occupies the equatorial. In this here, you can imagine and you can feel it out very easily that the repulsive forces in here, when the bulky group occupy equatorial, will be very much less. Got the point, Al-Bara? Wonderful, fine, wonderful, perfect. Okay, guys. Now, is there any other question, please? If there is any other question, I know this topic, it needs imagination because it's like three-dimensional structure. It's like this is actually part of what we call it stereochemistry, which is the study of molecules in three-dimensional view. So you need to imagine it. You need to think with imagination. But if there is any question, please let me know. There is no harm to repeat any aspect which you would like to know. Any other question, guys? Any question? Okay. If there is no question, I'll just continue. Now, in here, please focus with me just the last aspect which I'm going to mention before going forward with the slides. As you can see here, this is chair conformation, right? There is one movement, just for the compound. By the way, I just want to ask a fundamental question here. Why the compound will be in continuous moving? Why not to stay in the most stable conformation and that's it? Why the compound, or there is no compound in just one picture, in one conformation? It must be always, in continuous motion, but what we can say, there is one conformation is the most stable. Why this cannot be, just in chair conformation and that's it, without moving? Does anyone know? Why you don't prefer to stay still? Why? What about repulsion, Shayma? I mean, for yourself, just imagine, think of it easily. For yourself, what is better for yourself? What situation is more stable to you? To stay still like this, or just relax and move, continuous motion? Which situation just more stable, more relaxed, easier, better for you? Exactly, moving. Because fundamentally, you should remember in the general chemistry 102, we studied that in every situation, whenever we have more entropy, then definitely the situation will be more stable. So that means movement is always accompanied with stability. So that's why, although this chair conformation is the most stable, but this cyclohexane, or this ring here, will always, in continuous motion, will make some sort of ring flipping. This ring flipping here, this carbon, which was number 1, focus with the ring flipping, what's going to happen. And this is carbon number 4. In the ring flipping, carbon number 1 will be coming down, and the carbon 4 will become up. Do you see? Like this. This is what we call it ring flipping. This is actually most of the time the cyclohexane prefers to do. simply what we call it ring flipping. I want you just to focus again. What's happening or what's going to happen upon ring flipping? Upon ring flipping, remember here, we have the axial bonds. What's the color of the axial bonds, guys? What's the color of the axial bonds? Just answer, either writing or by mic. Yellow, exactly. The axial colors are the yellow ones. Now, what's the ring flipping? Again, the ring flipping is the carbon here, which was above the plane, will become below the plane. The carbon which was below the plane will become what? Above the plane. So let me just show it to you. So I will just push this down and this push this up. What's happened here? What's the color of the axial bonds here? Can you see it? You see? That's exactly the case here. Please remember this all the time, if you can see it nicely. Upon ring flipping of the cyclohexane ring, every axial becomes equatorial and vice versa. It is true. In other words, every axial becoming equatorial, every equatorial becoming axial. Is that clear, guys? So this is actually everything related to the chair conformation of cyclohexane and all aspects of this issue. Now we will just keep focusing. Instead of I may come back to the models for any reason if there is any question. So this is simply what you can see is a ring flipping. You see this carbon here, suppose this is carbon number 1, 2, 3, 4, 5, 6. What's going to happen by ring flipping, carbon number 1 will go down while carbon number 4 will goes up. So what's going to happen, this is carbon number 1, carbon number 2 is this is 2, this is 3, this is 4, this is 5, this is 6. Here. As you can see here, upon ring flipping, every axial which was in this color here, which was in the green color, becoming equatorial, and every equatorial which was the blue ones becoming axials. Do you follow me? That's actually always accompanied with what we call it a ring flipping, which is a natural behavior. It always happens. I mean, the cyclohexane is in continuous motion between these two, let's say, equilibrium, these two structural equilibriums, or the two equilibrium structures. Do you follow me, guys? Is there any question about the ring flipping? Any question about the ring flipping until now? Is there any question? Alright, perfect. So let's move and let's see certain situation. Now here, let's start with 3 situations. First of all, I know, and as you know, you don't have models, you don't have 3-dimensional structures to represent your answer. So you always need to express your views and thinking from 2-dimensional to 3 and from 3-dimensional into 2. Anyway, the first aspect I would like to teach you now, how to draw the chair conformation of cyclohexane. I'm just going to bring this closer to you. Don't worry, it will be in the other video, which is on the YouTube, will be more clear. But because of the camera in the laptop, it's not that much clear. Anyway, to represent the chair conformation of the cyclohexane, you need to draw 2 parallel lines. Just one is a little bit, they are offset from each other a little bit. So this is from here this is starting from here, then the other line here should start maybe a few centimeters away from it. So approximately both lines are the same. Do you follow me? So you just draw it this way. If you have a pen and paper, please just do it as I do it together. So just in order to be able, all of you, to draw the chair conformation of cyclohexane. So first, we draw these two lines, these two parallel equal lines, but as I said, they are not exactly above each other. If this starts from this point, then a little bit, few centimeters away from this point, while in here, it's a little bit the same thing, more than that side. You follow me? So this is the first step. The second step, you just now make the bond. Now, remember, we have these lines, or I'm just using another color. Remember that the end of these lines are carbons. Here, these are the carbons which makes the sitting of the chair. Do you follow me? So, the chair is always, we have 4 atoms or 4 carbons making like my hand. One atom is above, while the other atom is below. Do you follow me? This is simply the chair. This is exactly the same situation. You follow me? So in this case, all what you need to do, you just match or join these lines by making a bond this way, and this simply make this line by this way. Do you follow me? Is that clear how to draw that chair conformation of cyclohexane? Of course, I may keep repeating this forever, but without you trying this by yourself, it will stay always difficult. So please try it few times until you reach the point that you can draw the chair conformation easily and straightforward, like this. Something like that. So anything like that. So this is most likely the chair conformation. Do you follow me? Now, always the ring flipping, or the opposite to this, it's simply the opposite to the drawing here. So in this case, I may draw the line from this side and then to this side, and then I join them this way. So these two structures, or these two conformations, are what we call them the ring flipping to each other. This is here the ring flipping. As we said, upon ring flipping, every axial becomes equatorial and every equatorial becomes axial. So let's take the situation where we have mono substituted cyclohexane. So the first situation when we have mono substituted, and the example in here will be like methyl cyclohexane. When we have the methyl cyclohexane, these are the two chair conformations possible for the cyclohexane. So we will have only two options for the methyl to occupy. Either the methyl to occupy equatorial or to occupy the axial. So we just redraw it because alright, so this is actually, now the methyl here, if we have this methyl, this is methyl, alright, hydrogen, this is one possibility. So this is one conformation, or conformation 1 for the methyl. Or we may have the methyl here to be at this position. This is the second conformation, because as we said, every axial upon ring flipping, every axial becoming equatorial and every equatorial becoming axial. Yes, please.
I'm not sure I understood that.
What's this? Do you follow me, guys? Hello? Alright, perfect. Now, which of the two conformations is more stable, 1 or 2, and why? Which of the two conformations for monosubstituted cyclohexane is more stable? Conformation 1 or 2? 2, absolutely, as we said, because 2, the bulky group will occupy equatorial, which will be then free of 1,3 diaxial repulsion. While here, this methyl here will be, the 1,3 are these here. These are the 1,3. 1, 2, 3, there are hydrogens here. So there will be some sort of interaction. If the methyl here occupies the axial, then there will be some sort of repulsive forces with the hydrogens. Therefore, definitely 2 is more stable than 1. More stable than 1. As we said, every bulk group will prefer to occupy the equatorial position rather than any axial. Is that clear, guys? Is there any question about this point, about the mono substituted cyclohexane? Wonderful. Let's move to di substituted cyclohexane. And in this case, we'll take 1,2-dimethyl, for example. Let's take the situation where we have cis 1,2-dimethyl, because we said cyclohexane. So the situation here, we have the 2 methyls. What we mean by cis, we mean they are in the same plane. For example, here above, and this is above. Now, generally speaking, the best way to represent the stereochemistry is simply to use the representation of this representation. Here, always we mean by this here, it's above the plane. This bond means above the plane. And while this bond here, the dashed one, means below the plane. So in this case here, when we say cis, that means both methyls are in the same plane, which means either they are both above or they are both below. Do you follow me? So this is the compound what we want to draw, this most stable conformation of this compound. In this here, we have 2 methyls, and both must be cis, which means they must be in the same plane, the same phase. You follow me? Now, we have here, let's do 1 and 2. We have, as we have done before, let me just use different colors. I will just use the axial to be the green one. So we have 1, 2, and we have the equatorial to be 1, 1, 2. And this the same thing upon ring flipping. What's gonna happen that the axial becoming equatorial and the equatorial becoming axial. So this is 1, 2, and the second one will be 1 and then 2. Do you follow me? Now, we have here 2 methyls. So there is 2 options. The 2 methyls to stay cis, either the 2 methyls here to occupy, I'm just using the color of the methyls to be different now. Here I will use methyl, and this is methyl. So as you can see here, the 2 methyl, I'm sorry, these are trans, I'm very sorry. If I put the second methyl in here, in this carbon, it means the stereochemistry will be trans because they are in opposite directions. But we are talking about cis compound. So the cis here, the second methyl must occupy this equatorial. Do you follow me? So this is the first option. Is that clear? Is this clear for drawing the first option of the 2 methyls to be at 1, 2, and as well to be cis orientation? Maria, what's your question exactly? Just ask the question, please. I'm waiting you to ask the question, Maria. Okay, if you want me to repeat the whole issue, okay, let me focus on here. We are talking about a compound which is called cis 1,2-dimethyl cyclohexane. No, Maria, both one is axial, the other is equatorial. In this first conformation here, in order to draw the two methyls and they are both cis, Maria, and everyone else. In order to be both cis, you see, this methyl is oriented, where's the orientation of this methyl? It's oriented above the plane or below the plane? Just answer, please. Exactly. Now, what do you think about the second methyl to be cis? Should it be oriented above the plane or below the plane, the second methyl? Again, above. So look here, this is the first methyl, we're done with it. Now here, we have two bonds here. This is the above the plane, this is below the plane. Then for sure, this methyl must occupy this position. Got it, Mary and everyone else? So this is the first situation. So this is the first conformation. Do you follow me? Now, the second conformation, what we have, it simply is the upon ring flipping. Just make the ring flipping, which is the opposite. In this case, the first methyl will be equatorial. The second methyl will be axial. So, which conformation is more stable? 1 or 2 and why? Which conformation of the two is more stable? 1 or 2 and why? Just going to make this, in order not to make any confusion, just make the bond a little bit longer and then the methyl, in order not to make any confusion. Do you follow me, guys? Which one is more stable? 2 is more stable. Why? Jawahir and Mazen. Why? Okay, we will come to same. Which one, Jawahir and Mazen? You said 2 is more stable. Why 2 is more stable? Jawahir or Mazen? Why it's this repulsion, Mazen? You said 2 is this repulsion. Why 2 is this repulsion? Mazen, don't stop talking to me.
Because there is no hydrogen.
There is what? Jawahir, there is no hydrogen, you said?
Yes.
No, Jawahir, hydrogens are there always, you see, but we don't put them in order not to complicate the structure. Do you follow me? So when we said Jawahir and everyone else, when we say 1,2-dimethyl cyclohexane, that doesn't mean that this is hydrogen, here 2 hydrogens, here 2 hydrogens. Do you follow me? Here 2 hydrogens. Do you follow me, guys? The hydrogens are there, but I didn't draw them in order not to make the picture more complicated. I just want to show you just the methyls here. What's the occupation of the methyls? Because that's the most important thing.
I know that.
Right? So what do you mean then? Joanne, why you stop talking to me? Anyway, in both conformation, we have what we have here. For the methyl groups only, we have one methyl occupying axial and one methyl occupying equatorial. In this here conformation, we have one methyl occupying axial, the other methyl occupying equatorial. Do you follow me? So in both cases, there must be equatorial, there must be a bulk group occupying an axial position. So therefore, both are the same, because the same thing here. Both are the same stability. So conformation number 1 or 2 should have the same stability. Do you follow me? Is that clear? Alright, so that's why actually here, and just here we want to see which conformation is the most stable conformation. Let's move, actually in the second example, the picture will become more easy and even easier to understand. Let's just move to, instead of cis, let's take as an example the same compound but another isomer, another stereoisomer of it, which is the trans. Do you follow me? So we are talking about now about the trans 1,2-dimethyl cyclohexane, and the trans 1,2-dimethyl cyclohexane we represent it by this way. One is above, one is below. Do you follow me? Now, when we want now, again here I'll just remove the methyls and then insert them. I don't have space, guys, to draw or to write, but again we're talking about trans 1,2 cyclohexane, dimethyl cyclohexane. Do you follow me? Now, when I want in the first structure here, in the first conformation, I need to look here. I need to put the two methyls at carbon number 1, carbon number 2, also with one condition, that these two methyls must be trans. What does that mean, the trans? What's the meaning of trans, guys? Just write down. What's the meaning of a trans? I'm just waiting answers. What's the meaning of trans? Or what do we mean by trans? Exactly, Maria, perfect. So it means they must be both in opposite planes. Yani, if one is above, then the other one must be below. Otherwise, it will never be trans. Got it? That's actually how you think of it. Now, if I don't have a choice, it's just you start up with certain point. If you choose to put the methyl here, where should I put the other methyl? At the axial or at the equatorial? What do you think? In order to keep it trans, should I at the axial? Because otherwise, if I add the methyl here, it will be cis. But in here, we're talking about the trans. So this is the first option, that the two methyls are diaxial. Hajar, if I put the other methyl here, you see the relationship, this is above, this is above. That means both are the same. So you are talking about cis, not trans. Got it, Hajar? Perfect. So there is no other option rather than to put them both at this orientation. Of course, the other one, opposite to this, both of them will be diequatorial. I think it's very obvious now which conformation will be more stable conformation. Conformation number 1 or 2 and why. Just write down, please. Which conformation will be the more stable conformation and why? Absolutely. طيب, Jalila, Amani, yes, perfect. It's 2. Conformation number 2. But why? Why conformation number 2 is more stable than conformation number 1? Because in conformation number 2, both bulk groups occupy equatorial, while here both bulk groups occupy axial. What does that mean? If the bulky group occupy axial, we should expect that there is more repulsion forces, and therefore structure number 2 is way much stable compared to structure number or conformation number 1. Is that clear for the time being? Clear? Any other question? Because that's actually the end of the topic here. Let's say the most important aspects of the topic, we have discussed them. If there is any question, please let me know. Otherwise, we will end up our lecture. Any question, guys? I will wait. Right. 30 seconds to receive any question if there is any. All right. Thank you very much for attending, and I wish you a very pleasant and nice day. Inshallah, see you next Monday. Thank you. يعطيكم العافية.